The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week on Science for the People, we talk about towers, bridges, sinking cathedrals, and other feats of structural engineering. Roma Agrawal is a structural engineer who has worked on structures from footbridges and sculptures to train stations and skyscrapers, including London's iconic tower, the Shard. She's a tireless promoter of engineering and technical careers to young people, particularly underrepresented groups such as women. She's advised policymakers and governments on science education and has given talks to thousands around the world. And she's here today to talk about her first book, Built: The Hidden Stories Behind Our Structures. Roma, welcome to Science for the People.
Oh, thanks for having me.
So why or when did you decide you wanted to become an engineer?
Really late, actually. I wasn't one of those people that knew exactly what I wanted to do from a very young age. So I always knew that I loved maths and I loved science. I come from a reasonably nerdy family. So my mum studied science and maths at university. My dad's an electrical engineer. And, you know, the four of us, and my little sister included, we used to spend our Sundays making and breaking stuff. So we had Lego and Meccano and all sorts of different toys. And even through school, I really enjoyed studying science and maths. And it was always the subjects that I was much better at. And I kind of went through my school years then really not sure what I wanted to study when I went to university or anything, but I decided to do physics. And I really enjoyed the physics, but I couldn't quite see myself going off and doing a PhD or, you know, kind of longer term work in academia. And I just by chance happened to do some work experience over a summer in the physics department at my university, but I was actually surrounded by engineers and I was so fascinated by all the work that they were doing. So they were designing the particle detectors for CERN, which is that big particle accelerator that kind of sits under swathes of, I think it's France and Switzerland. So I mean, it was so super cool. And I could see them kind of solving problems on all sorts of scales. So they were trying to think of how to design a holder for a tiny lens, all the way up to how we're going to transport this big piece of equipment. And that's when the kind of it just hit me that engineering is all about using creativity and using your maths and your science skills to solve problems. And I was completely sold at that point.
I love hearing from nerds who came to STEM careers late, because I think there's this myth to STEM careers that if you don't get started early, if you're not super into math or like know that you want to be into a STEM career early on, that you've kind of missed the boat. And it's just not true.
Yeah, no, I totally agree with that. So, I mean, I changed my mind halfway through my physics degree. So I actually finished my physics degree. I did 3 years of physics and then I went off and I did a 1-year master's in structural engineering. And I think what was really cool about having a physics degree is that, you know, I picked up the prospectus for university and looked at all of their engineering courses. And I was like, I could actually do any of these because I'd learned all the basics and the fundamentals as part of my physics degree. So the application of that could have gone into any field of engineering. I happened to choose structures. I don't really know why. I think I had this kind of underlying fascination with buildings and skyscrapers. At some point during my life, I had wanted to be an architect. So it all just kind of seemed to fit together. So the architect has to have a much larger scale vision. So they need to think about what the building, say, is going to look like. How big is it going to be? How many people is it going to accommodate? What's it going to be used for? And all of those decisions come from understanding the context of the city or the town that you're creating this structure in. So you might look at, you know, what's in the surrounding neighborhood, what's in the wider city. So you look at this kind of large scale and then you drill down into, okay, well, I've got this piece of land. What is that piece of land therefore going to be? The structural engineer, on the other hand, is, well, how do we actually make this stand up? So an architect might kind of sketch a triangular pointy skyscraper on the back of a menu, which is what happened with the Shard. And then what the engineers have to come in and do, the structural engineers have to look at that, work with the architects and say, well, this is how I'm going to add, I always say I'm adding the bones to the flesh. Mm-hmm. So you've got this vision, this idea, the kind of aesthetic, and then we're kind of trying to look past that to the skeleton and say, well, how are we going to actually make this stand up so that it can work to resist gravity, sort of kind of force that pulls something down, and then the horizontal forces, which is wind everywhere, but sometimes can also be earthquakes. So we have a much more technical role to play.
I do want to talk a little bit about your sort of first big project that you designed, which was a footbridge. Because that section of your book quite delighted me because I could feel your excitement at kind of getting to walk on your first sort of big public structure. I can only imagine what that must have been like.
Yeah, so that's my little bridge baby. It's a footbridge which joins together two different parts of a campus of the Northumbria University in Newcastle in northern England. And I started working on that project on my 22nd birthday. So, it was a very, very memorable kind of experience for me. And I think the other really wonderful thing about it is that from the time I started my design work on it to the time it finished, it was only 18 months, which is also quite unusual for engineering projects, which tend to be quite long term. And I also was in a very, very small team. So it was just me and my boss. And, under his direction, I basically designed the steel, the concrete, the cables, the underpass to allow cars to go in. And so it's kind of just allowed me to touch all different aspects of structural engineering within the first 18 months of my career. So it's a really, really special project. And, as you say, you spend months looking at stuff on a computer screen, doing hand calculations, doing sketches. When you actually go on site and you see those pieces of steel being delivered, you see them being lifted in, connected together, painted, it just kind of blows your mind, because I always find that the structure looks so much bigger than I ever expected it to be. So there's this weird kind of scale thing you need to get your head around, and it's just amazing. And I think another kind of weird phase, and this is probably true, I guess, for bridges as well, but particularly for buildings, is that there's a point at which, you're one of the very few people allowed to actually go into that building and have a look around and have a walk. But then suddenly one day it opens and it's not yours anymore. It becomes everyone else's. And that's kind of a strange feeling as well.
Sort of like releasing it into the wild, kind of.
Yeah.
So what type of bridge was the Northumbria University footbridge, your very first big project?
So it was a cable-stayed bridge. What that means is that you have a big mast or a big column that tends to be fairly tall, and then that's supported on some nice, strong foundations, which are generally made of concrete. And then kind of emanating from that large pylon or mast are cables. And you can arrange those cables in lots of different sorts of ways. So, if you kind of search out images of cable-stayed bridges on the search engine, you'll see lots of different arrangements of the cables. But they all basically have the same principle behind it, which is that the cables hold up the bridge deck. So the bridge deck is, the surface that you're walking on. The force kind of travels up those cables, and then those cables are connected, as I said, to this mast. And then the mast basically gets squashed. So it's compressed, and then that force goes down into the foundations and gets dissipated into the ground. So we talk a lot about load paths in structural engineering, and what that means is tracking where the forces or the weight of stuff, materials, people, whatever it might be. How does that weight track itself through the structure? What's the path that it's taking? And so cable-stayed bridges have that specific load path. So weight of bridge deck goes up into the cables are stretched, they're in tension, you compress the mast and the foundations, and that's how that system works.
So why pick a cable-stayed bridge for this particular situation? Was there something about a cable-stayed bridge that suited this particular place?
Yes, absolutely. So we were crossing a motorway or a highway, and you can get large trucks and all types of different vehicles driving down that road. And so we were very constrained as to where the structure of our bridge could actually go down to. So we had to leave a clearance. I can't remember exactly what it was, but say it was 6 meters, and we couldn't go below that. So that means that and then we also tied into the levels of the existing kind of pathways on each side of the bridge. So we took the top of the pathways that existed and we took, the bottom of the zone that we were allowed to build in, and that gives you a zone within which you can fit your structure. And that zone was really thin. So, if you imagine a log bridge where you literally just stick a piece of, a bit of tree across a stream, that kind of bridge, which is what we call a simply supported bridge, so that the clue's kind of in the name, it's just simply supported across 2 points. They tend to be quite deep. What the cable bridge does is that it absorbs some of the weight up into this mast, and so it means that the thickness of the deck can be much, much less than you would with a simply supported bridge. So that was our biggest constraint, is we need to make sure that the vehicles traveling on that road didn't get anywhere near our structure.
Right. You definitely don't want something like a truck running into the bottom of your foot deck. That's not a good plan. No, that sounds like a terrible idea. And you mentioned in the book as well, and you talk through kind of not just the structure we're going to build and how, what it's sort of the science behind how it's built and where the forces go, but also the considerations of how are we going to put this thing together that has kind of minimal impact on, the motorway that's running underneath it, because obviously you can't shut that down for 18 months.
Exactly. And so again, this was one of those kind of doses of reality that hit me when I started working, is that it's all very well designing a structure on your computer program or, your piece of paper, but it doesn't just magic itself into place, It has to go in phases. It has gravity to contend with. It has other forces going on, push, pull from the wind, so on. So when you think about my footbridge, which was a cable-supported deck, we would need to put that deck in before we could put the cables, or the other way around. There has to be some sequencing that is considered. So we said, okay, we're going to put the deck in first. We're going to support the deck at its two ends. But the deck, like I've said, is not designed to span that entire distance. It needs the cables to hold it up. So what we did was we put a big temporary column or support in the middle of the motorway, between the two directions of traffic, and we protected it, so that if there was collisions, the forces wouldn't cause that column to topple over. And then we used that to support the bridge about halfway across its span. Now, if you look at my footbridge and the cables, it's actually got 3 points of support from the cables, and I'm only giving it 1 point of support during construction. The reason that works is because you won't have the full load for when the bridge is finished, because we're not going to let hundreds of people onto the bridge while it's only got that one support. So you have a restricted loading phase, and then we come in and we put the cables in and we tension them up. So we make sure that they're all nice and tight. And once all of that's configured, we can come back and remove the column. So the disruption was only over a couple of weekends. So there was one weekend where we put the stuff in, the column in, we had to close the motorway for that. We then kind of did our work above the traffic. And then when we finished, we, closed a few of the lanes again to take the temporary column down. And, that is such an important, especially for bridges, deciding how you're going to build it has to be done right at the beginning of the project. Otherwise, you might come up with a form of bridge that's not buildable.
That definitely sounds like a terrible idea. And of course, if we look in the history books, there have definitely been some disastrous examples of bridges not built properly. I'm thinking of the one in particular that you highlight in the book, which is the Quebec Bridge disaster.
Yeah, so that, even till today, is the most lethal civil engineering disaster that's happened. So 75 people, all men in fact, died while they were constructing it. So this was exactly an example of a situation where, the engineer that was working on this project basically got the maths wrong and kind of underestimated the weight of the bridge. And so while it was being put up, it couldn't hold itself up. And, pieces of the bridge that were supposed to be nice and robust and holding it up just folded like paper and caused the steel to collapse. And, with it took 75 of the men working on it.
It's so sad to see these kinds of things happen. And there's a lot of things that we have to take into account with bridges as well. I know there was and I can't remember the name of the bridge. There's a famous example of resonance. There's a video where you can see the bridge just like waving as there's, I think, cars and people going across it, which is just, it's a surreal video. I'm sure many people have seen it, but watching it is just such a surreal thing because it doesn't look real. It doesn't look like this could really be something that a movie that wasn't just in a random kind of Hollywood movie.
Yeah. So I think the one you're talking about is the Tacoma Narrows Bridge, which was, I should say, in Washington. And this was the era where engineers were really pushing the envelope with how far they could span a bridge, with how slender, how thin the bridge could be. We were starting to create these really long suspension bridges. So suspension bridges, like cable-stayed bridges, hold up a deck using cables. The difference with the suspension bridge is that the load path, so that the pathway for the way the loads find its way down into the foundations is a bit more complicated. You have more cables involved. And so the Tacoma's Narrow Bridge was one of the pioneering bridges of its day. And not soon after it opened, pretty soon after it opened, rather, people could see that there was a problem. Like, it did bounce around a little bit and it was a little bit disconcerting. And then one day it wasn't even a strong storm. It was a fairly, mediocre storm, as storms go. It just set off this, what we call a galloping or fluttering effect. And what that means is, so every object has a natural frequency, and that means that it will vibrate at a particular frequency. So imagine you're pushing a child on a swing. The number of swings that, happen per second is the frequency. And what you'll notice is that if you, periodically and constantly keep pushing the child on the swing, as the child comes to the point that's closest to you, you apply a force and then the child will swing further. But it doesn't matter how far the child swings, the number of swings per second still remains the same. So your frequency always remains the same. But the force can basically create a much larger movement. So we had this wind hitting the Tacoma Narrows Bridge and it set off its natural frequency. It started to vibrate, and then somehow, the frequency with which the wind was kind of buffeting the bridge meant that it made the amplitude or the movement bigger and bigger and bigger and bigger until it basically ripped itself apart.
Oh, just the idea, structural engineering, it must be such a thing to have on your mind as you're designing a structure, that it is something that's going to be used by people, perhaps housing hundreds, if not thousands of people potentially, if we're talking about very tall skyscrapers, or bridges where, thousands and thousands of people a day go over it. Motorway bridges where potentially, hundreds of thousands of vehicles go over it every day. It's a career and a job that definitely has a real physical kind of life and limb impact on the world.
It is, and it's quite humbling when you think about it. It's very humbling when you see things go wrong, because it really reminds you that, you have a big responsibility as a structural engineer. I think it's also really important to focus on the fact that these disasters don't happen that often. That's why they make the news, and, rightly so. And we absolutely need to be thinking about structural engineers and structural engineering when things are going right, which is, most of the time, because otherwise we just take it for granted and forget about it. And then when things do go wrong, and they tend to go wrong, if we're pushing the envelope, if things haven't been tried and tested properly, if there's a mistake, if there's shoddy building involved. And, when these things go wrong, it is absolutely imperative that we as structural engineers study that, learn from it, and make sure it never happens again. This is definitely something I've found from all of the engineers that I know from a multiple different set of disciplines in engineering, and something that I really appreciate in the personality of an engineer, which is there is a desire to, when something goes wrong, to learn as much as possible from it and to not have that thing go wrong again. If a disaster has to happen, let's hopefully only have it happen once. I know a good example of this is the Ronan Point Tower, which you highlight in the book as well, in London. And that was a fascinating thing to read about. I had not heard about what happened to this tower. And it's quite an interesting
way for a structure to fail, which is kind of unexpected, especially if you don't know the kind of structural engineering side under the wall or beneath the walls, I guess.
Yeah, and I think what's also interesting about this, which is obviously an awful thing because people lost their lives in this, was that it wasn't just about the engineering. It was also about the social context at the time, which kind of drove a particular way of building. So to set the scene, we were coming off the back of the Second World War and, soldiers are coming back. You're now come into peacetime. So life is very different. The population starts to increase and suddenly we're needing to build lots and lots of housing really quickly. And the solution that was thought about at the time was to do some prefabrications. What that means is you create some of the structure, you build it or manufacture it in a factory, and then you bring those pieces to your construction site, and then you kind of lift them up and put them into place. And that's much quicker than trying to put wet concrete and allowing that to harden. So they basically almost built it like a house of cards. So you had panels, the panels formed the walls, the panels formed the floors, and they were quite rapidly joined together. And they built, I think it was just over 20-story building. And a weakness was inherent in that whole process, which is that the way all these different panels were joined together was not very well tied together. It wasn't very robust. And so one day, one of the residents, I think it was on level 18, lit a match to put her gas hob on. So she wanted to make some tea. And there was a boiler, which was supposed to heat up her water and provide her with gas for cooking. And it had been leaking gas. So that was another factor that is kind of unexpected. So she lights the match, all of this gas catches fire, causes an explosion, and this explosion blew out some of the walls of her apartment. Now what was interesting about all of this was that her eardrums were okay. And our eardrums are quite susceptible to explosions. But what this showed was that the pressure that was needed to push these walls out was even less than the pressure that's needed to, perforate our eardrums. So it really wasn't much pressure. But because some of the walls had been blown out, the levels above had nothing to support them, and they came crashing down, and they basically took out the entire corner of that structure. And I think it was 4 people that lost their lives in that tragedy.
What I find extra fascinating about this is both how you mentioned that it wasn't actually that much pressure. It wasn't enough to hurt the person who lived in that building's eardrums, but it was enough to blow up part of the wall. And also that it was able to cause so much damage even though it was higher up in the building. I remember as I was reading the section of the book, I had somehow forgotten that it was higher up. And as I was reading, I'm like, oh, it must have, been a lower flat in the building. And then everything just kind of tumbled down from on top. But actually she was high, and it caused this kind of chain reaction down the whole side of the building.
Yeah, that's exactly right. So in fact, people have considered the fact that if this explosion had occurred much lower down in the building, then you would have had the weight of many more stories kind of pushing down on those walls, which means that the friction at these poor joints would have been higher, which means it probably would have needed a lot more pressure to blow out the walls. So there is a theory that actually had this happened, on level 1 or 2, that the walls may not have blown out, but because she was up towards the top of the tower, there wasn't so much weight, therefore there wasn't that much friction between these different panels. They blew apart at a lower pressure than what would have been required lower down in the building.
Just a interesting kind of confluence of the right things going wrong in the worst way. It was quite fascinating, and it sounds like as well that engineers took a lot from that experience and have now changed the way we join prefabbed buildings on site, because we still do use prefab techniques where we build bits of buildings and then bring them to the site and kind of assemble them on site. But we have definitely used that disaster to try and make that process better.
Yeah, so this idea of disproportionate collapse was born after the Ronan Point disaster. And what that means is that if you do have an explosion or you do have some problem with the structure of a building, the damage that happens as a result of that shouldn't be out of proportion, to the cause. So at Ronan Point, you had an explosion on one floor and we lost an entire corner of a building. So that was a disproportionate failure compared to its cause. So what we now need to do is to consider that. So when we design our beams and columns, our floor plates, or if we're doing prefabricated building, whatever it might be, we tie stuff together much better. So these junctions are much more robust. You will tend to use wet concrete or big steel bolts to, tie it all together so that they can't be ripped apart as easily. And so it absolutely, this is a good example of a disaster which led to widespread change in design. And I guess the World Trade Center was the next time that we saw such an, awfully dramatic, disproportionate effect on a structure.
That one was also quite interesting to read about in your book, because we do try and build buildings, especially buildings that are potentially higher targets for attacks, for bombings, that kinds of things. Structural engineers do make an effort to make them as resilient as they can. So you tell a story about the Bombay Stock Exchange bombing and how that building was not disproportionately destroyed because of a bomb that went off. Whereas with the Twin Towers, we saw a catastrophic failure of those buildings, even though hypothetically there was some reinforcements to accommodate the hole that had been punched in the side of the building.
Yeah, so, so what was really shocking and sad about that situation was the fact that, so the structure had actually been designed to deal with the impact of a plane, but at the time that it was designed, the biggest planes were smaller than the plane that actually impacted it later. So that was one thing. And then secondly, because there was so much fuel in the planes, the fuel actually caught fire. And it was a kind of a failure of the fire protection to the steel that was holding up the tower that allowed the steel to get, just way too hot. And the hotter steel gets, the less strength it has. And so at some point it just could no longer hold up the weight that it was being expected to carry, and it failed from there. So again, the lessons that have been taken away from that, is about, well, how do we account for catastrophic events like this, and also protecting the escape zones for the people, the occupants, in a much more robust way.
Yeah, one of the big things that we've done is to reinforce the escape routes, because that was one of the big problems as well with that tragedy, was that people couldn't escape. They couldn't get and make it to an escape. So one of the takeaways, it sounds like, is we are thinking about that as we're building things like elevator shafts and stairwells to make sure that they're as protected as possible, and that those pieces are able to stay structurally sound and are more resistant to fire, to at least allow people to escape a building.
Yeah, absolutely. So, that's a big consideration. So this is one of the things that I think architects look at, which is really fascinating, is, how many people are actually going to be in the building at any one time? Where are they going to be? How will they move up and down a building? So I talk a bit about the story of the lift and Otis in my book, and the fact that skyscrapers didn't actually exist until we could move up and down them easily. So the movement of people within structures is a really, really important thing to consider when we're designing things.
Both the kind of everyday, day-to-day use, but also in catastrophes. It's
Absolutely.
like the Titanic not having enough lifeboats. You gotta have enough velocity to get people out quickly.
Yeah. And, at the same time, like you say, with the day-to-day use of a building, you don't want to be standing in a line waiting for your lifts and elevators all day, so you need to think about how you're moving people, on an everyday basis as well, so that it's not inconvenient.
Yeah, elevators are really such a fundamental piece of the puzzle we needed to be able to build the types of skyscrapers we have now. I mean, nobody is going to walk up all the stairs to get to the top of the Burj Khalifa. I mean, I don't even think you could walk up the stairs to get halfway up the Burj Khalifa and not need to be pretty fit.
Yeah, I think so. So we have this thing in London where people run 42 stories. We have a 42-story tower, and people run up the stairs of that for a charity, to raise money and so on. I think people do it in 4 or 5 minutes, and it just completely blows my mind.
Wow.
So maybe those people don't need lifts, but I definitely need them.
I would be actually curious to see what the Burj Khalifa emergency escape routes look like, because if you're at the top of that tower and something goes wrong, if you can't use the elevators, it's going to take you a long time to get down to the bottom.
Yeah, so you're quite right that a lot of these tall buildings nowadays, they do include the lifts in the escape strategy. So we're so used to seeing all these signs saying don't use the lifts in case of an emergency. But actually in some of the more modern skyscrapers, you're quite right. You do have to use them. You might not use them all the way down, but you might use them for a portion of them. But yeah, I mean, I love the story of Otis. So Elisha Otis was this kind of mechanic / tinkerer / person that worked in factories, and he was working in a factory in New York, and he was in his 40s at this point, and he had to kind of move lots of materials from one level to the other. And he starts saying, well, you know, I've got a bad back. I'm not getting any younger. There has to be a cleverer way to do this. And so he basically designs this system. So I mean, look, lifting platforms have existed for thousands of years. And, you know, going back to the Romans again, they used lifting platforms to get their gladiators from, you know, the lower levels of the Colosseum up into the fighting arena. But they were just held up by ropes. And if the ropes snapped, then the platform plummeted and probably killed the people that were standing on it. And clearly this wasn't something that, you know, Otis was going to allow for. So he wanted to come up with a system where, you know, it was safe, so that if the ropes did snap, there would be some kind of braking mechanism in place in order to prevent it from plummeting. And that's what he did. So in pure engineering terms, his invention was a fairly simple one, but it just hadn't been done before. So he created this system where he had some feet, kind of bits of wood that stuck out sideways, and then he changed, you know, the rails, the guide rails that tell the lift, you know, how to stay in a straight line as it's going up and down. He changed them from being smooth to toothed. So when the rope snapped, some springs would kick into action, and these feet would kind of lodge themselves into these toothed rails and keep the lift car in place and stop it from falling down. And he demonstrated this at a huge, you know, industrial expo in the 1850s or 60s. And then from there, he made his name. They installed the first ever lift he designed in a skyscraper in Manhattan. I think it was actually only a 10-story building or 12-story building. But it started from there. And even now, when I take lifts and escalators around, you know, the London Tube, our underground train system, you see his name there because his company still exists, which I just think is such an amazing legacy.
It's such a great story as well, because the way he demonstrated it at this event was, of course, to get on it himself and then have someone kind of dramatically chop the rope that was supporting the elevator, which is just such a fantastic kind of fair kind of atmosphere, right? You've got almost like a sort of like a circus show. It's you come one and all and see the amazing Otis and his lifting platform. It kind of has that showy vibe to it, which I really love.
Yeah, I mean, he must have really made an impression. People probably remembered him. So they say that, you know, as this rope was dramatically cut, as you say, and the platform kind of starts to plummet and then it shudders to a halt. And then he puts his arms out and says, "All safe, gentlemen, all safe."
Oh, I love it.
And, you know, so yeah, very, very, very theatrical.
That guy definitely knew how to work a crowd for sure.
Yeah. Yeah.
I do want to talk about the Shard because it's such an iconic building in London. I've been up it myself and I really love for anybody who's not been up it, there's a viewing platform at the top that is open to the sky. And that I didn't expect, but it's such a lovely space up there to kind of look around London, but also there's air coming in and it feels like such an open space, which is very cool.
Yeah. So that space isn't for looking around London, right? You need to go up there and you need to look up at the steel. That's what you need to do.
I did that too. It is such a beautiful space. And the way it's been built up there is so gorgeous. I really enjoyed, I mean, usually when I go up to tall buildings and kind of I view the scenery and then I kind of come down. But we actually hung out there for quite a while because it was just such a pleasant space to be in, which was nice.
Yeah, I mean, it's one of those really unusual places where the structure was all on show. So in buildings particularly, so I would say with bridges, we tend to show off the structure and you can see it. In buildings, you tend to want to cover it up. And you know, architects and people don't want to see exposed steel and concrete necessarily. I personally am a huge fan, but that's just me. So the opportunity to design what is essentially a 20-story building that was completely open to the elements and all the structures completely exposed. So you can see every last bolt and weld up there, was an amazing challenge, because we've talked about construction. How is it going to be built? It's the tallest steel that we've ever done in the UK. And at the same time, you have millions of people visiting this viewing gallery, and they might look at the steel. And so you want to make sure it looks pretty good. So as a structural engineer, I think I sat in between these two aspirations. One was it has to look amazing. The other one was we need to be able to build this safely. And as a structural engineer, I had to kind of bring those two together. That was really the highlight for me of working on the Shard.
Did you get a chance to go up there while it was still not entirely finished?
Yeah, so I went up to level 87 a number of times. You can't go up there anymore unless you are going to get into that terrifying window cleaning cradle. And unless you're really good with heights, I wouldn't recommend it. But yeah, so I used to go up to level 87, which is actually the highest floor plate. And I mentioned in my book that it's quite a small floor plate, because obviously at this point, the Shard, which is a tapering kind of pyramid reflected type, it's a kind of stretched pyramid type shape. The floor's pretty small, and I'm not that good with heights. So I would kind of get to the top step and I would just stay there. I wouldn't kind of go out onto the floor plate because it just felt a little bit too exposed to me.
I'm one of those people that likes heights if I feel safe in them. So one of the things I did do at one point in Toronto was do the CN Tower edge walk, where you can go outside and you get tethered up, and you can do things like lean out over the edge of the tower and put your weight against the tether, which was just fantastic. But you definitely have to be okay with heights.
Yeah, you talking about that makes me feel sick.
You have to trust the equipment you've been given, which coming from a theatrical background where I did some rigging work, I did trust the equipment because I knew how it worked and I knew what kinds of redundancies are put into them. But
sure.
It was really cool. We had a great day for it. But going back to the Shard and talking less about heights, there was some interesting things about the Shard when it was being built, in particular about how it was built, because that building was built by both digging down and building up at the same time, correct?
Right. So we call that methodology top-down construction, and exactly as you describe it, you're digging down to create the basement and the foundations at the same time as you're actually building the tower itself. So the reason we did that was to save time. And when you save time, you save money, ultimately. So that was really the driver. So we started off at the ground floor and we put the piles in. So the piles are the big concrete kind of cylindrical bits of structure that go into the ground, and they're what hold the building up. So they're the foundations of the structure. So we put those in at ground level, which is a bit weird considering the fact that we wanted to go 3 levels down to create a basement. But bear with me. So we put the piles in. We also then did something rather strange, which was to basically plunge these huge steel columns into those concrete piles. So these steel columns were nowhere as deep as the concrete piles. They were just as deep as our basement and a little bit more. And then we cast the ground floor with a big hole in the middle. So if you imagine like a donut. And then we basically started digging downwards. So we kind of burrowed underneath this concrete slab that we installed, and we kept digging deeper and deeper, and we kept putting in slabs of these various levels of basement. And at the same time, we had our rig, which is called a slip form. And what the slip form does is it's like a giant, if you imagine like a cookie cutter. So this slip form basically forms, it's got walls. I'm not explaining this very well. Let me start this one again.
Yeah, for sure. Some things are hard to explain without a picture.
Without a pen and a paper. So we attached this rig. So in order to move upwards, we created this rig called a slip form. And what the slip form does is it creates a kind of a mold. So if you imagine like you're pouring cake batter into a mold because you want a particular shape for your cake to come out. So we create these walls and then we can pour the wet concrete in, and that's where you get your structure from. So this can basically move up continuously. So it's on hydraulic jacks and it rises very slowly. So we were doing about 3 meters of height every 24 hours. And that was happening. So that was going up at the same time as we were still going down and completing the basement. So we ended up at this amazing point where there were 20 stories of this internal kind of concrete structure, of the tower built, but the foundations hadn't been quite completed yet.
That sounds so, fabulous. And I'm assuming that as a structural engineer, it's not just figuring out how as we talked about with the bridge, it's not just figuring out how the final structure is going to handle all of the forces and supporting itself and not coming down, but also how a 20-story building is going to support itself without a full and complete foundation.
Yeah. And so those, I said earlier that we put those slightly strange steel columns inside the concrete piles. That's what those steel columns were doing. They were acting like stilts to hold the tower up while we were kind of digging down into the basement. So once the foundations were finished and once all the walls were finished, those steel stilts basically became redundant. We didn't need them anymore. They still live in there in the shard, but they're not doing anything anymore. But we needed them. We needed that structure in order to be able to build the thing.
I assume, in particular with London, where, for people who don't know, there is so many tunnels and infrastructure under the ground in London, potentially more than almost any other city. There is so much happening underneath the sort of street level of London. When you're putting and looking at building something like the Shard, and you're looking at sinking piles into the ground, I mean, that must be a bit of a job in and of itself to figure out where is safe to sink piles and to what depth.
So whenever people ask me what's the most difficult thing about structural engineering or building in London or whatever it might be, that is always my answer. It is building in the middle of a busy city is the most difficult thing. If you're just going to build a tower in the middle of a desert or a big field, it's much easier. So the thing with the Shard was that the architects and the developers and the funders, they all knew early on, because these are the checks that are done even before a site is purchased, that there were no tube lines directly underneath that piece of land. Mm-hmm. So there was a lot happening around the site, but there was nothing much happening directly below the site. So that's why it works. That's why the tower in that location does really well.
Sorry, I was just going to say, I'm assuming that's one of the things restricting our ability to build up in London in the same way that Manhattan is built quite tall, is that there's so much underneath it that you can't just plunk a skyscraper anywhere.
So that's one reason, but another reason is also the fact that the soil in London is basically clay, and it's literally like the clay you imagine you make pots out of. So it's quite soft, it's quite malleable. As the seasons change, the amount of water in the ground changes. That makes the clay shrink. It makes it expand. It does all sorts of weird and wonderful things. Manhattan's on rock. So you can just go in and plonk towers up. I'm sure there's going to be engineers from New York calling me up going, it's not that easy. It's easier than London, let me say that.
At least that bit is, for sure.
Yeah.
Foundations and the different types of ground underneath a building are so critical to the way a structure is built, but also the potential longevity and what will happen to that structure. There is a fascinating case study you talk about in the book of a cathedral in Mexico City, which I found just completely riveting. That one had me completely riveted, and now it's a place that I want to visit because it sounds like such an amazing engineering challenge and space to be, in addition to being an old kind of cool cathedral.
Yeah, so Mexico City, now the Aztecs, a few hundred years ago were kind of walking around, and they had this, this is a legend or a myth, but they had this sign that from their gods which said you will establish your new city where you find this symbol. And the symbol was an eagle sitting on top of a nopal cactus with a snake in its beak. And the flag aficionados among you will realize that that's the symbol on the Mexican flag. So they basically wander around looking for this symbol, and, lo and behold, one day they come across it. The fact that it was in the middle of a lake didn't seem to deter them.
Which, impressive. That would deter most people, I think.
Yeah, and maybe it should have. I don't know, because what they then did was, we talked a little bit about sinking piles. What they did was they took giant timber logs and they sunk those through the water down into the nice strong level of soil that they had at the bottom of the lake. And they essentially built almost a floating kind of suspended little town in the middle of the lake. And that was the start of Mexico City. So a couple of 100 years later, when the Spaniards arrived from Europe, they came in, they took over the city, and they started to want to expand the city. And so they started filling this lake in with soil and mud from the surrounding area. But you can pretty much imagine that if you fill in a lake with soil, that water is not really going to go anywhere. So the soil underneath the center, the oldest part of Mexico City, is extremely soft. It's extremely wet. And the result of that is that that area of Mexico City has sunk by about 3 stories in the last 100 years.
That's so huge. That's almost, I feel like you could almost stand and watch it sink.
So luckily, it has really slowed down now, because I guess you put a lot of weight and then it kind of all wants to kind of squash down, but now it's much more consolidated. And they also try and remove a lot more water now when the water levels start to increase. So there's a much more sophisticated mechanism to try and control that now. But the result of this huge amount of sinking that's happened in this city is really strange. So you walk around and you see doorways which should be rectangular, but they're not. They're at a funny angle because the buildings have sunk at strange angles. So this particular cathedral that I talk about in Built was the Metropolitan Cathedral, and it's in the Zocalo Square in the center of, old Mexico City. And it was built by the Spaniards, and it was built on top of some Aztec pyramids. So it was built on a giant raft. That's what we call the type of foundation, which basically means a big slab of stone or concrete or what, a combination of the two. And it literally kind of, if you imagine a big flat log raft, on very soft ground, it would sink, but it might also tilt. So that's what happened here. Because you had old Aztec pyramids and old structures below this cathedral in some parts of it, but nothing under the other parts of it, it sank unevenly. So at one point, the back corner of this cathedral was 2.5 meters higher than the front corner of the cathedral. So I'm about 1.5 meters tall. So what's that? That's like 5'3". So this is not quite twice my height, but just to give you an idea of scale, it's a lot.
That's a significant amount in one building. And cathedrals are big spaces. They're quite large, but at the same time, that is, that's a noticeable hill you're walking up from one side to the other.
It is. It absolutely. And, there are these lovely towers that flank the cathedral, and, they were tilting. And at some point people said, this is getting to be a real issue. And we're going to lose the integrity of this cathedral if this carries on. And so, here come the engineers to save the project. And they did something that I found extremely counterintuitive. So even as a structural engineer, I just thought this is kind of bonkers. What they did was the bit of the cathedral that was the highest point. Well, so actually they dug these kind of big wells, you can call them, underneath the foundation. So they went through the foundations of this cathedral, built these wells, okay? And then the corner of the cathedral, which was at the highest point, they started to extract the soil. They took soil away from the ground underneath the foundations. And they took more ground away where the cathedral was higher and very little ground from the points which, were much lower. And what that did was to allow the soil to kind of consolidate and squash under the weight of the cathedral and tilt it back. It didn't tilt back completely to flat because at that point they were slightly worried about the amount of material they needed to take out of the ground. They decided that the towers were now vertical enough that they would remain stable. So there is still a slight angle to that structure.
The idea of going under a structure like that and pulling out ground so that it sinks farther in certain places is, like you say, counterintuitive and a little bit terrifying is the wrong word, but I went, really? Like bonkers, I think is a great word. Word you used.
And then, so one of the great, so they're monitoring it now. So I loved going around the cathedral because it's a beautiful cathedral and it's got all the stuff you want to see in a cathedral, but it's also got science. So I was walking around looking for there's a pendulum in the center of the cathedral, and the pendulum has, so it's a big weight hung on a string. And as the cathedral's been tilting and sinking in all these different ways, people have been marking where that pendulum has pointed. And that's a way of tracking how much movement you're getting, what kind of movement you're getting. They have pressure pads under some of the columns. They're checking that what are the loads in the columns, are those changing? Because that might indicate something's moving again. So they have all of the scientific equipment, which is basically sending data to, I think it was a lab in Italy, who are looking at it and monitoring it to make sure that it's not getting any worse. So what they've done is they've managed to get it to a point where it now settles evenly. So the whole thing is sinking quite uniformly at just a few millimeters a year now. So it's a much, much slower rate. So they're keeping an eye on it, but it's looking pretty stable now.
Such a fantastic story. There's Mexico City is kind of an interesting space structurally because it's built on a lake, essentially. But also it's quite prone to earthquakes. And so this has made them have to do some creative engineering with things like towers in order to make them structurally sound enough to withstand earthquakes. And also their sinking city. Yeah,
so the earthquake thing can have a really devastating effect on the city. Because what you want to imagine is you've got a bowl with jello in it and you're shaking that bowl and the jello's kind of wobbling everywhere, but there's buildings on top of that. That's the kind of effect that happens. So you get an earthquake, but the kind of the response, the amount of movement you get in that bowl of jelly, as it were, it's much more than you would get in a normal city. So what happens, it was completely fascinating. I don't actually think this made it into my book, but the earthquakes tend to originate from, I think it's the southeastern corner of Mexico. And the speed of the wave of the earthquake is slower than the speed of sound. So the moment an earthquake hits the southwest corner of the country, an alert is sent to Mexico City to say, you have an earthquake coming. And then the people of Mexico City have the matter of a few seconds, the sirens will blare, and people will evacuate, just like I said, a few kind of tens of seconds before the earthquake actually hits them. So there's this kind of absolutely fascinating system in place to try and minimize the amount of, damage caused to people from these earthquakes.
To basically buy people a few extra precious seconds to get out of as much as possible harm's way.
It's just incredible.
So how does one build a skyscraper in a place like Mexico on a bowl of jelly? Because that sounds like a nigh on impossible task. But if I look at pictures of Mexico City, there are clearly skyscrapers there.
Yeah, so the large majority of the skyscrapers are not in the bowl of jelly because Mexico City has now expanded far beyond that initial lake. Mm-hmm. And the ground outside the original footprint of the lake is much more stable. But yes, you still get earthquakes. So the example that I find really interesting is the Torre Mayor, which is one of the tallest towers in Mexico City. And what they did in that was they used a hydraulic system. So if you imagine your car pistons with the oil in it, and you put energy into it, and it can move, and it's quite a slow, gradual movement. It absorbs energy. That's what the kind of system that they used on the outside of this tower. So they braced this tower. They put a structural kind of exoskeleton on this tower, which keeps it stable against wind. But these pieces of bracing, this kind of steel structure, is actually made from pistons, or dampers, as we would more normally call it. So if an earthquake hits, basically the pistons or the dampers start to move. But because you've got this kind of thick, viscous liquid, that's going to, kind of absorb the movement, absorb some of the energy, the amount of movement that you get in the tower is much less than you would get if it was just a normal kind of solid skyscraper. So I think that that's a really, really innovative way to deal with earthquakes. And, the story goes that there was an earthquake, a fairly severe one, not long after the tower opened, and that the people sitting inside couldn't really feel how bad that earthquake was because the system worked so well.
That's pretty high praise to those engineers.
Yeah. No, so it's a really impressive tower.
I find, in general, the way we dampen the forces in particular tall towers to be quite fascinating. I've spent a number of evenings probably reading about tuned mass dampers. They're so interesting, and the way they work, and the idea of putting something that massive on the top of a tower and the way it counteracts some of the force. I find that just eternally interesting.
Yeah, so I'd talk about another example, which is the Taipei 101 tower in Taiwan. And that's a really tall tower. So that's over 500 meters high. And you get typhoons there and you get earthquakes there. So it's a really challenging environment to build towers in. And exactly as you say, they have a giant tuned mass damper that hangs towards the top of the building. So what all of that means is that when the building starts to sway, it's like a giant pendulum at the top of the tower. So if the tower sways right, this pendulum, because of its mass and because of the inertia it carries, will swing left. And it basically swings in the kind of the opposite direction to the way the tower is going to be swinging. And it basically absorbs that sway. It kind of cancels it out and really reduces the amount of sway that you get. And that's what essentially keeps it safe from the typhoons and the earthquakes that it experiences.
And these, in particular, this mass damper, like when we say mass, it's quite large. This is not a small thing. This is a huge amount of weight that's being used to kind of counteract the sway of this tower.
It is. I think it kind of spans a few stories, like it's 2 or 3 stories large, as it were. And another way, so that's a big weight. The other way you can do it is to use big tanks of water. So the water will basically slosh in the opposite direction, out of phase to the swaying. So that's another way that it can be done as well. And on bridges as well, we often use them. So, the kind of disaster we talked about with the Tacoma Narrows Bridge, with the wind-induced vibrations we got there, you get a type of tuned mass damper that you can stick on the bottom of a bridge. And again, because of the weight and the springs between the bridge deck and this weight, the springs basically kind of absorb some of that movement as well.
So just before we end, I'm curious if you have any thoughts for people who maybe haven't given structural engineering and the structural engineering around them too much thought, and what types of ways they could start to more notice or appreciate some of the engineering that just is around them, because we're surrounded by it, big and small.
Yeah, I mean, structural engineering is such an intrinsic part of our lives. We spend most of our lives inside some form of structure or building. So we wake up in our homes. We might take a train through a tunnel to work. We then go into an office building, or we're in school, or whatever it might be. We spend a large proportion of our waking hours and sleeping hours, in fact, inside these covered structures. And I would really encourage people to do a bit of digging, find out a little bit about their homes, find out what materials it's made from, think about what's below you. You can actually find soil profiles just on the internet quite often. So you can figure out, well, what kind of soil actually lives below my house. You can think about what kind of forces act on your house. So, do you have earthquakes? Do you have strong winds? We've always got gravity. That's an easy one. And then think about the materials, because, we didn't talk that much about materials today, but I could spend another hour just talking about steel, about concrete, about brick. They are such fascinating subjects in themselves. Find out more about what your structures are made of. So there's just so much to learn and to look at. And hopefully you'll be able to appreciate your daily life with a new lease of light to it.
I totally agree. There was so much in this book that I did not know. Things like how a bunch of the sewer systems are created. You don't really spend a lot of time thinking about how what happens in your house gets, the waste that you create kind of gets out into wherever it goes. You just know that it leaves your house. And there's a whole structure underneath everyone's feet, that manages that. And there's engineering involved in that. And you mentioned as well the materials. I found that we didn't touch on it here. We didn't touch on so many things that are fantastic in the book. But I remember being surprised, by a historic brick recipe that you had. I had no idea bricks had to dry for 2 years. I had no clue that
if
brick
you lived in ancient Rome, those were sometimes the rules.
Yeah, and that I found quite surprising, the idea that you would have to build the bricks that you would need 2 years out. So if there's a big project coming, hopefully someone 2 years before built enough bricks to keep you going. Like that, those kinds of challenges and some of the history on steel, and it's all entirely fascinating. And unfortunately, we are out of time, but that just means people should go and get the book and learn about it themselves.
Yeah, I think that's a good idea.
Roma, thank you so much for your time today. It's been fantastic.
No, thank you so much for having me.
If you want to learn more about Roma Agrawal, her book, or her work as a structural engineer, we have links to get you started available in the show notes for this episode, which, as always, you can find on our website, scienceforthepeople.ca. Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.